Okay, picking back up in 8.1. So last year we covered 8.1, which is setting up the recurrence relations, and then 8.2 is how to solve them. Actually find an explicit formula where you could just plug in, let's say you wanted to know how many moves would it take to solve the Towers of Hanoi problem with 10 disks. Well, if all you have is the recurrence relation, you can't figure out 10 until you figure out 1 through 9, all right? But with an explicit formula, you can just plug in the number 10 and you got it. So that's what they do in 8.2. Now the problem is we're a little behind where we were last year. So I was thinking, okay, is it more important to show them how to set them up or to show them how to solve them? And I think the answer is it's more important to show you how to set them up, especially since Maple can actually solve them. And so what I'm going to try to do, and it's been actually a very long time since I've used Maple to do this, so I was looking at help before I came over, and I think I can make it work. I'll show you how you can put the recurrence relations into Maple and just have Maple solve them. That's fine. Okay, so I'm not going to go over this part again. This was the very last thing we did. We talked through why is this the recurrence relation for the number of moves. It's basically because, let's say you have 10 disks. You move the top 9 disks from, say, peg 1 to peg 3, and the number of moves it takes to do that is h sub 9, right? The same number of moves it takes to solve the puzzle with 9 disks. Then you move the largest disk to peg 2, so that's one more move, and then you have to move the 9 disks over to peg 2 on top of the big one. So that's another h sub 9, all right? So h sub 9 plus 1 plus h sub 9 is 2 h sub 9 plus 1. Or in terms of n, it's h sub n is 2 times h sub n minus 1 plus 1. And then I remember I pulled up Excel and I was showing you how you could do it in Excel just using, refer to the previous cell and use that as the value of h sub n minus 1. So the next thing I was about to show you was it turns out it's pretty easy to actually solve this one explicitly. And remember that h sub 1 equals 1 because you can solve the puzzle in one move if there's only one disk. All right, that's not a lot of fun. All right. Okay, so if you can follow this, they start with h sub n is 2 times h sub n minus 1 plus 1. And then they take h sub n minus 1 and substitute 2 times h sub n minus 2 plus 1. So that gives you 2 squared h sub n minus 2 plus 2 plus 1. Okay. Then they substitute for h sub n minus 2, 2 times h sub n minus 3 plus 1, which gives you this. And then you distribute this stuff and you get 2 to the third h sub n minus 3 plus 2 squared plus 2 plus 1. And you keep on doing that until you get all the way down to h1. And in the end, you end up with this little geometric sum, 2 times 2 to the n minus 1 plus 2 to the n minus 2 plus blah, 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 plus 2 plus 1. And I feel like I should show you why this equals this. I can't remember if we ever did that before. Well, you could do that proof by induction, or you could even do it this way. Here's an easier way to do it. Yeah, kind of. Okay, so let's say I want to know more about this 2 to the n minus 1 plus 2 to the n minus 2 plus blah, 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 plus 2 plus 1. And I'm going to call that S for sum. And now what I'm going to do, actually I'm going to leave a space. I'm going to multiply both sides of this equation by 2. So when I multiply both sides of this equation by 2, 2 times 2 to the n minus 1 is 2 to the n. And 2 times 2 to the n minus 2 is 2 to the n minus 1, all the way down to 2 times 1, which is 2. All right? And now what I'm going to do is subtract this from this. And almost everything is going to cancel. 2s minus s is s. These cancel, these cancel, these cancel. The only things that don't cancel are the 2 to the n and the minus 1, right? Because there's a minus sitting out front of this whole thing. So that's kind of cool, I think. All right. But yeah, it is geometric. It's kind of Calc 2 type stuff. So yeah, it takes 2 to the n minus 1 moves to solve the puzzle if you have n disks. And then this story, yeah, this is just stolen out of the book. A myth created to accompany the puzzle tells of a tower in Hanoi where monks are transferring 64 gold discs from one peg to another according to the rules of the puzzle. The myth says that the world will end when they finish the puzzle. So the question is, how long will that take? Let's say it takes them 1 second to move a disc. Well, it's going to take 2 to the 64 minus 1 seconds, which is this many. And if you translate that into years, it's 500 billion years. So we should be good for a while. All right. The world should survive a while longer than it already has. That reminds me, you guys got to hear this story. I just love this. So my graduate school advisor, who's a very interesting guy, it was his birthday yesterday, and he's one of my Facebook friends. So I can always count on him to make some kind of interesting observation. So yesterday morning on his birthday, he says, today I am 2 to the 3rd times 3 squared years old. And you can figure out what that is. And then he says, the next time that I will be p to the q times q to the p years old for distinct prime numbers p and q, he says, I'll be 800 years old, at which time I probably won't notice. That's like classic. He says stuff like that all the time. Very interesting guy. This just reminded me of that, this sort of understated, you know, very dry humor. Very typical of math types. All right. So, some examples of recurrence relations. Find a recurrence relation for the number of bit strings of length n that contain 3 consecutive zeros. All right, well, you can start off by looking at some initial conditions. All right, let me just peek at something here real quick. Don't look, spoiler. I just want to check my notation. Oh, I have this in a separate thing. Hold on. Here it is. Just checking notation. Okay, A sub n. All right. Is this my pen? I don't like it. I don't like that one either. They started ordering these new pens that seem to wear out a lot faster. Yeah, you know what? The black one is pretty good. Okay, let A sub n equal the number of bit strings of length n that contain 3 consecutive zeros. Okay, so the first few values are really easy. How many bit strings of length 1 contain 3 consecutive zeros? None. Yeah. What about length 2? None. What about length 3? 1. 0, 0, 0. Okay, so now the recurrence relation. This is an interesting thing. Takes a little getting used to. Let me just black this out for a second. There we go. Okay. So I'm going to separate the string. Now I'm on the case the string has length n. Okay. So there are 3 cases I want to look at. If the string starts strings starting with 1. Start with 1 first. If the string starts with a 1, that does not help you get your 3 consecutive zeros. All right. And so you'd be looking at a 1 and then a whole bunch of blank spaces. The number of ways to fill in those blank spaces so that you get 3 consecutive zeros is a sub n minus 1. The number of bit strings of length n minus 1 that have 3 consecutive zeros. That makes sense? In other words, let's go to the case where the string has length 4. If your string starts with a 1, then the only way to fill in the rest so that you have 3 consecutive zeros is like this. 1, 0, 0. There's just that one. Okay. The next case I want to look at.
0, 0, 0, 1.
Hmm?
0, 0, 0, 1.
No. It starts with, I'm saying if it starts with a 1.
Oh.
Right? So yeah, this is for length 4. Okay. So the next case I'm going to look at is if you might think, well, now look at strings starting with 0, but you can't just look at strings starting with 0 because the 0 it actually is helpful to getting 3 consecutive zeros. So you have to break it off into 1 more, or actually 2 more little cases. Next, look at strings that start with 0, 1. 0, 1. Zero, 1 is also completely unhelpful for getting 3 consecutive zeros, isn't it? So if your string starts with 0, 1, then you have to fill in those remaining spaces with a string that has 3 consecutive zeros. And how many of those are there in terms of n? Not a sub n minus 1. A sub what? A sub n. What? What? I thought I heard somebody faintly whisper the answer. N minus 2. That's right. You used up the first 2 spaces. You have n minus 2 left. Okay. There's one more unhelpful case that I want to look at. What if your string starts with 0, 0, 1?
Is it at least 3 or exactly?
Or no, at least 3. At least 3. Yeah, at least 3. Good question, yeah. Contain 3 consecutive zeros. Yeah, that means at least 3. I bet exactly 3 is a lot harder. Okay, totally unhelpful for getting to 3 consecutive zeros. So you start with 0, 0, 1, and then how many ways are there to fill in those last spaces? You got this. A sub n minus 3. Okay. Now, there is only one more case we have to look at. If your string does not start with a 1, and it does not start with 0, 1, and it does not start with 0, 0, 1, what do the first three spaces have to be? They have to be all zeros, don't they? Right? Because we already took care of the, well, let's look at the possibilities, right? There's 8 different possibilities, really, for what the first three can be. It can go 0, 0, 0, 1, 1, 1, 1. This is like my truth table. 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. So starting with 1 takes care of all these. Starting with 0, 1 takes care of these two. Starting with 0, 0, 1 takes care of that one. The only one left is that. And this is totally different. If your string starts with 0, 0, 0, think about this carefully. Now you've got your 3 consecutive zeros. How many ways are there to fill in these remaining spaces so that you have 3 consecutive zeros? Well, it's not exactly infinite, right? You have, you're kind of along the right lines, though. You only have a limited number of spaces in there. So I think there's only a finite number of ways to fill that in. So how many is that?
2 to the n minus 3.
Say it again.
Oh, sorry, 2 to the n minus 3.
Good. 2 to the n minus 3. In other words, you can put whatever you want in those spaces. You can put a 0 or a 1 here. You can put a 0 or a 1 here. Put a 0 or a 1 in all these spaces and put a 0 or a 1 there. Because you can fill in the rest of those however you want, including all 0 if you want to, because it is at least 3. At least 3 consecutive zeros. That makes sense? I want you to meditate on that for a little bit. So starting with 1, totally unhelpful to get the 3 consecutive zeros. The number of ways to get 3 consecutive zeros in n minus 1 spaces is this many. Right? Start with 0, 1, also completely unhelpful. The number of ways to fill that in so that you have 3 consecutive zeros is this many. Same for this. But then this one is totally different. Since I've already got the 3 consecutive zeros, I can fill in these spaces any way I want. So that's 2 to the n minus 3. So the recurrence relation for a sub n, well, first of all, it's got the initial conditions are a1 is 0, a2 is 0, a3 is 1, and then for n greater than 3, a sub n is equal to a sub n minus 1 plus a sub n minus 2 plus a sub n minus 3 plus 2 to the power n minus 3. So if you ask me how many bit strings are there of length 11 that have 3 consecutive zeros, I can't answer that off the top of my head until I have the values A1 A4 through A10. Right. So I want to play around with something here for a minute. First of all, I like Excel because I use it all the time, so I'm pretty good at it. Although there are certain things I don't know how to do. I asked Professor Kanemoto to help me with a project that we're working on, for example. Okay, where is that button? I just had it. Right here. Okay. So first thing I'm going to do is bring up Excel. Bigger. Okay. So in my, well, let's do this. I'm going to put my n values over here. And we'll just take a whole bunch of those. I think I said, well, just as many as will fit. And then over here, this is going to be a sub n. So remember, the initial conditions were 0, 0, 1. Okay, so here's what I'm going to do. I'm going to do this with a formula. I'm going to say, starting at n equals 4, I want this to equal the last value plus the second to last value plus the third to last value. Right? And then I need to add 2 to the power n minus 3. And of course, n is this number right here. So I'll just tell it to look at that number. Okay. So for n equals 4, let's think about this for a second. So you have 1, 0, 0, 0, that's one of them. You don't have any that start with 0, 1 or 0, 0, 1. But if it starts with 0, 0, 0, 0, I'm sorry, 0, 0, 0, then the last number can be a 1 or a 0. So you should have a total of 3. Right? You should have 1, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 1. So there's your 3. And now if you just copy this formula down into however many cells you want, okay, it gets big pretty quick after a while. For example, 1,121 strings of length 11. Make sense? All right, I want to try to do this in Maple. All right. Bear with me because this was literally right before I walked over here. In fact, I searched for help on how to solve recurrence relations. I remembered the command was rsolve. You know what? Let's just do this. I'll bring up Maple. Okay, where are you, Maple? And rather than go into my email to grab the syntax that I copied and pasted, we'll just get it from here. I hope this works. Okay, so I want a new worksheet. All right, first thing I'm going to do is search for help on rsolve. So do question mark rsolve. And you've probably noticed in these help things that you can skim them. All right, there's a whole bunch of stuff that you don't need. All right, I usually just look for what are the arguments. All right, so equations, functions, and then some kind of optional thing at the end. Single equation or set of equations, function name or set of function names. All right, so I remember the one that I thought we would be able to use. We have initial conditions. They give you examples of what happens if you put it in without initial conditions, like this one here. F sub n equals -3 f of n is -3 times f of n minus 1 minus 2 f of n minus 2. It writes the recurrence relation in terms of f of 1 and f of 0 because I haven't told Maple what those values are. All right, so it's saying once you figure out what f of 1 and f of 2 are, once you figure out your initial conditions, I'll tell you the exact formula. So that's like on this next line, it put in the same recurrence relation, and this time it said, how did they put this in? F of 1, I have to look at the screen, I can't tell what that is. F of 1 dot dot 2 equals 1. So that's just a really lazy way of saying f of 1 and f of 2 are both 1. All right? So let's try that. I'm just going to copy this into my worksheet. Except I'll put the, okay. So our recurrence relation is f of n is equal to f of n, what did I do? F of n minus 1 plus f of n minus 2 plus f of n minus 3 plus 2 to the power n minus 3. And over here, I think I want to tell it that f of 1 and f of 2 and f of 3 are all equal to 0. Or f of 1 and f of 2 are 0, f of 3 is 1. Okay, so let's see if this works. Oh my goodness.
Oh, that looks nice.
Yeah. It worked. All right. It's just that this is it's a really ugly formula. So they're saying r is a root of the polynomial z cubed plus z squared plus z minus 1. And in terms of that root, which is probably some ugly complex number, the thing looks like this. Oh my gosh, that's awful. All right.
Glad you think so too.
You know what? Let's try it with the Towers of Hanoi one, because that one is a lot prettier. All right. So that recurrence relation was h. Oh, I can see. I got to put a bracket here. H of n equals 2 times h of n minus 1 plus 1. And the initial condition was h of 1 equals 1. And then close curly brackets, and then in another set of curly brackets, tell it to call that h. Ah, that's much better. H of n equals 2 to the n minus 1, just like we got before. Okay. So it did that one really easily. All right. So I figure by showing you this, I don't feel as guilty about skipping 8.2, where it shows you how to actually solve these by hand. And not even all of them, just certain ones. All right. Okay. That makes sense? So the most important thing is just know the command is rsolve. And I'm thinking maybe instead of you doing homework on 8.2 the way that I used to do it, I'll just give you a few of them to do in Maple. That's all. That's good enough. All right. Okay, so back to this. So we've kind of already answered all these questions. The initial conditions are the 0, 0, 1, right? These are the initial conditions. And then how many bit strings of length 7 contain 3 consecutive zeros? Well, my Excel answers that. Right? So if you just put it in using the formula, go down to where it says 7, and there are 47 bit strings of length 7 that contain 3 consecutive zeros. Okay? Make sense? Otherwise, you have to do it by hand. Which isn't awful. I mean, you know, it might take you about 5-10 minutes. All right, let's see what's next. I should let you think about this one for a few minutes. There's only a couple of little things that are different. So now we're doing ternary strings, which means 0, 1, or 2. 0, 1, or 2. Okay. String can contain 0, 1, or 2. And we want to know how many of those contain 2 consecutive zeros. So what I want you to try to do is try to adapt what I did with the binary strings. Try to adapt that to the ternary strings. Okay. So ternary means contains zeros, ones, and twos. All right. Think about the different cases that you have to count separately. All right. And then we'll compare notes here in about 5 minutes. Hit pause on this. So we can actually worry about let's worry about the initial conditions after we get the recurrence relation, because the recurrence relation actually gives you a hint on how many initial conditions you need. All right. Okay. So I want to think about what are the cases that we have to count. Instead of starting with 1 or 0, 1 or 0, 0, 1 or 0, 0, 0, what should we count? Like, for example, I think we should still count starting with 1. What else should we count? Starting with 0, 1. And what else? 0, 0. But I think there are a couple of others. A couple of other things are unhelpful towards getting 2 consecutive zeros, since this is a ternary string and not a binary string. For example, it would also be completely unhelpful to start with a 2, and it would also be completely unhelpful to start with not a 3, there are no 3s. There are only 0s, 1s, and 2s. 0, 2 would be unhelpful. So that's how it's different. Okay, so if you start with a 1, that's just like before. The number of ways to fill this in is exactly the number of ways, the number of strings of length n minus 1. So that's a sub n minus 1. And what if it starts with a 2? How does that work? How many of these should there be? It should be the same thing, right? If you start with 0, 1, that's just like before. You have n minus 2 spaces left. So the number of ways to fill those in with a string that contains 2 consecutive zeros is a sub n minus 2. And same thing for starting with 0, 2. Okay, but then if your string starts with 0, 0, you have, this is like earlier when it started with 0, 0, 0. All right. I've got my 2 consecutive zeros. So are there any restrictions on how to fill that in? There are not. How many ternary strings are there of length n minus 2? 3 to the power, well, you have 3 choices for what to put there, 3 choices for what to put there, da 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 da. There's n minus 2 of these, so it's 3 to the n minus 2. It's really, really similar to that one, right? You just have to use, 3 possible things instead of 2. So the number of ways to finish that is going to be 3 to the n minus 2. So your recurrence relation is going to be, we might as well just say this is 2 times a sub n minus 1. We can say this is 2 times a sub n minus 2. And then this will be 3 to the n minus 2. Okay. So the next question is initial conditions. How many initial conditions do you think I need? I only need 2 this time, because this recurrence relation uses the last 2 values. So as long as I start with 2 given, I can calculate all the rest of the ones I want. All right. So you remember how this works? How many ternary strings of length 1 have two consecutive zeros? None, right? How many ternary strings of length 2 contain two consecutive zeros? How many? One. Just the string 0, 0. And that's all you need. All right? I'm not even going to bother solving this one in Maple because I bet it's awful, just like the other one. But I will put it in Excel because next thing it wants to know is how many ternary strings of length 6 contain two consecutive zeros. So I'm going to bring my Excel back up. And let's see, I think I will just start again over here. Okay, so my initial conditions are 0 and 1. And then starting at n equals 3, the way that I figure it out is I go 2 times the last value plus 2 times 2 values ago plus 3 to the power n minus 2. And notice that n is right over here. Okay. So let's see if we can figure this out before I press enter. So the number of ternary strings of length 3 that contain two consecutive zeros, well, there's one starting with a 1, 1, 0, 0. There's one starting with a 2. There aren't any that start with 0, 1. There aren't any that start with 0, 2. But I think that there are 2 that start with 0, 0, or 3 that start with 0, 0. There's 0, 0, 0, 0, 0, 1, 0, 0, 2. So when I hit enter on that, it should say 5. Yay! And now if you copy that formula down, this one is going to be even bigger than the last one. Lots and lots bigger.
So the normal way you have to do it would be to plug in the initial numbers and then keep doing.
You would have to do A3, A4, A5, and then A6.
It would just be a lot of recursion, right?
Yeah, yeah. It wouldn't take you very long. It would just be tedious. That's all. All right, so look at that. Number of ternary strings of length 6 that contain two consecutive zeros is 281. And I do not want to see the explicit formula for that. Again, I'm sure it's awful. So we'll just leave that. All right. Questions? Okay. So I'll bring up the last example. We'll take a little break. Just think about it for, well, during the break. Bus driver pays all tolls using only nickels and dimes by throwing one coin at a time into the mechanical toll collector. Find a recurrence relation for the number of different ways the bus driver can pay a toll of n cents. And so, yeah, I thought this was what they meant. When they said throwing the coins one at a time, I figured they were trying to say order mattered. So, for example, if the toll is 15 cents, throwing a nickel and then a dime is considered different than throwing a dime and then a nickel. Okay?
Okay.
Now, the first thing that's a little tricky with this is just the fact that your recurrence relation is for multiples of 5, right? So 5, 10, 15. We don't care about 1, 2, 3, 7, 11. We don't care about any of those. So the nicest way to do that is kind of sneaky. You say something like, let A sub n be the number of ways to pay a toll of 5n cents. Isn't that sneaky? And then you can plug in numbers for n like 1, 2, 3, 4. Okay. All right. So
Oh,
yeah.
question. It didn't seem to be a function when I just did a little bit of it, because you can make, for example, 10 cents with 1 dime or 2 nickels.
That's correct. And so so that means a sub 2, which is 5 times 2. That's for 10 cents. That will equal 2. The number of ways is 2. A dime or 2 nickels.
Oh, okay.
Right? Okay. I don't know what happened here. I guess I did. Okay. All right. So, but it's a good idea to start looking, at the small number possibilities. So 5 cents means n equals 1. There's only one way to pay a toll of 5 cents, and that's with a nickel, right? Okay. And then, like Peter pointed out, for 10 cents, there are 2 ways. You can pay it with a dime, or you can pay it with 2 nickels.
Oh, okay. It said n cents there, but you're saying 5 in there?
Well, yeah, I'm using, a sub n is the number of ways to pay a toll of 5n, 5 times n.
Okay, that's a much harder problem. How do you pay a toll
Oh.
2 cents, for instance?
Yeah, yeah. Oh, I didn't even notice that. Yeah. I wonder if that's a typo.
Gosh, I hope so.
Let's just make that 5n. I don't even want to think about it. I'm sure there's a way to do it, but. Oh, yeah. Okay. That's better. Okay. All right, now we can start trying to be recursive. When you get to 15 or any higher amount of cents, you have 2 choices. You can either make your first coin a nickel, in which case the number of ways to fill in that blank is going to be the number of ways to pay 10 cents. Right? And the number of ways to pay 10 cents, we're calling that a sub 2. Right? But you can also make your first coin a dime, and then you fill in the rest of it with the number of ways to pay 5 cents. So in general, when you get to any amount higher than, let's say, starting at 15 cents, the number of ways to pay that toll is going to be the number of ways to pay the smaller toll plus the number of ways to pay the 2 smaller toll. Does that make sense? 2 smaller.
Nailed it.
Right? Okay. So if we're trying to pay 5n cents, we could either start with a nickel, and then the number of ways to pay the rest of the toll is a sub n minus 1. Or we can start with a dime, and then the number of ways to pay the toll is a sub n minus 2. So the recurrence relation is going to be a sub n is equal to a sub n minus 1 plus a sub n minus 2, which might look kind of familiar. You know any other recurrence relations that look like that?
Yeah.
The next to calculate the new number, add the last 2. That's Fibonacci, right? But it has different initial conditions, right? It doesn't start with a 0 and a 1 or a 1 and a 1. It starts with a 1 and a 2. which is actually still Fibonacci, it just doesn't start. A1 is 1 because there's one way to pay a toll of 5 cents. And A2 is 2 because there's 2 ways to pay a toll of 10 cents. All right, that one is almost. And how many ways are there to pay 45 cents? Well, that's not going to be, that one you can figure out really fast. This one I would probably do, okay, put the values of n maybe here, and then maybe next to that on the left or something say, how much money is that? I'm going to insert a row up here. So here's the value of n, and this is going to be the number of cents. So that's just 5 times whatever's here. Okay, so one way to pay a toll of 5 cents, 2 ways to pay a toll of 10 cents, and then for any n greater than or equal to 3, you just do the last value plus second last value. And if you copy that all the way down, that is exactly the Fibonacci sequence. And the number of ways to pay a toll of 45 cents is 55 ways. Okay. Since we're not going to get to do it, I thought it might be fun to show you this one. It's also in the book. Show you the actual explicit formula for Fibonacci numbers. I hope Maple doesn't do something silly with this. All right, so let's see. It's ACE, or we'll call it f of n, equals f of n minus 1 plus f of n minus 2, comma, f of 1 equals 1, f of 2 equals 2. And we'll call that f. Okay. Well, that looks kind of familiar to me. This is the explicit formula for the Fibonacci sequence. So, if you, roughly, I mean, it has it starts with a 1 and a 2 instead of a pair of 1s or a 0 and a 1. But it is that ugly. I knew it was that ugly. But what's interesting, and I remember telling you about this once before, this number here is the golden ratio. 1 plus the square root of 5 over 2. I forget where that came up. I remember it came up in here about 3 weeks ago, and I don't remember why. Anyway, and it's golden ratio is very closely related to Fibonacci numbers. As you crank out a bunch of Fibonacci numbers, the ratio between any consecutive 2 gets closer and closer to the golden ratio. Let me show you. So if I do over here, I'm going to say, what is this number divided by this number? So it starts out at 2. And then if you do that for a whole bunch of them, okay, it says they're all 1.6, but that's only because it's rounding. Okay. Starts to settle down somewhere around 1.618. Golden ratio, that 1 plus the square root of 5 all over 2. Look at that, 1.618, 0.33989. So those ratios are getting closer and closer to that number. All right. Okay. So I always use this as an example when I cover 8.2, which we're not going to cover this time, and I actually show you how to solve the recurrence relations by hand. I always use this as an example. It's ugly, and actually it's much easier for a computer, I think, to calculate Fibonacci numbers just using the recursive formula. Because all it's doing is adding, all right? It's not having to do any of this stuff. All right. If you need the 1,000,000th Fibonacci number, you would probably prefer to do it this way. All right. I think, yeah, that's all I have for 8.1. So homework is all posted for 7.1, 7.2, 8.1, which is all we covered so far, right, since the exam. Okay, so now give me just a minute.
And when's the homework due?
I'm not going to collect the next homework until the next exam. So you've got a little bit of time. Not as much time as you usually have between exams, but what's today? Today is the 26th. Next exam might be in about, well, it'll probably be in about 2 weeks, give or take. I'll let you know next week. All right. So probably all we're going to get through today, I'm going to jump into chapter 10, which is graph theory. And that's a lot of fun. I have to put up the notes for 10.1 though. Give me just a sec. Okay, so if you refresh your Blackboard page, you should see at the bottom 10.1. All right, graphs. So as you're going to see here in just a second, graphs has nothing to do with, graph the equation y equals x squared. That's not what we're doing. It means something totally different. This is 10.1. Graphs are discrete structures consisting of vertices and edges that connect the vertices. Different kinds of graphs depending on whether edges have direction, whether multiple edges can connect the same pair of vertices, and whether loops are allowed. So we're going to define all those things. I would really like to see, I'm going to skip ahead. Okay, so that's an example of a graph. This graph represents, I think this is supposed to represent whether there is a flight between two cities or something. Whether a particular airline has a flight between two cities. Or maybe it's that whether there's a highway connecting two cities or something. Okay, that's what we're talking about when we talk about graphs. I thought this was fun. Problems in almost every conceivable discipline can be solved using graph models. Here are a few examples. Competition of different species in an ecological niche, who influences whom in an organization, outcomes of round-robin tournaments, acquaintanceships between people, collaboration between researchers, telephone calls, links between websites, maps, and a whole bunch of others. Right? Okay. All right, so here is the official definition of a graph. A graph consists of a set of vertices and a set of edges. Each edge has either one or two vertices associated with it called the endpoints. Edge is said to connect its endpoints. when you draw a graph, you generally try to draw edges so they don't cross. All right, now there's a whole interesting topic, I think we'll probably do 10.7, called planar graphs, P-L-A-N-A-R. A planar graph is a graph that can be drawn without edges crossing. A graph that cannot be drawn without edges crossing is called non-planar. All right? So that's a really cool and very important application of graph theory. All right, if you're doing electrical work and you don't want wires to cross, all right, you might want to study planar graphs. Generally try to draw edges so they don't cross. This is not necessary because any depiction using points to represent vertices and any form of connection between vertices can be used. This is something that takes a little getting used to with graphs. Let's say that I draw one graph that looks like this. Let's say there's 4 vertices, and I'm going to call them A, B, C, and D. And let's say that these are connected, and these 2 are connected. Let me see, is that what I want? Yes. Okay. What I want to emphasize to you is that this is the exact same graph, even though it doesn't look the same, as if you had B and C switch places. So if I put C here and B here, and I keep A and D where they are, so A and D were connected, A and C were connected, D and B were connected, and B and C were connected. That is the exact same graph. The only thing that matters is which vertices are connected. All right? So that and that are exactly the same thing. Just imagine that these are like pins pushed into a cork board, you know, a bulletin board, and you pull them out and just switch them, and there's like rubber bands connecting. Yeah?
So if that were like a 3D graph, then the wires wouldn't be crossing. They would just be underneath each other. Yeah, that makes sense. But the point is that you can redo it so that one isn't even hovering over top of the other one. All right, and that's interesting. Speaking of 3D, so you're used to seeing people try to draw 3-dimensional things on, 2-dimensional pieces of paper. This right here is a graph. Let me see, that has one more vertex. Okay. So you can think of the vertices as being like the vertices of a cube, and 2 vertices are connected if there's an edge between an edge of the cube between those 2 vertices. All right. That graph has a name, and I want to say it's called I think it's called a cube. Q3, which means like 3-dimensional cube. Q2 would just be a square. I'm a little rusty. I haven't brushed up on that part of it, but pretty sure that's right. Okay. So again, this and this are exactly the same graph, same exact graph. And again, the key point is the way you draw a graph is arbitrary as long as the correct connections between vertices are depicted. So make sure that the correct vertices are connected. I know this is very wordy. It's just copied out of the book. Note that each edge of the graph representing this computer network, what computer network? Okay, I'm going to have to double check that. Connects 2 different vertices. Maybe that's the picture on the next page. No edge connects a vertex to itself. Furthermore, no 2 different edges connect the same pair of vertices. So a graph in which each edge connects 2 different vertices and where no two edges connect the same pair of vertices is called a simple graph. So it does make sense for certain applications to allow vertices to connect to themselves. All right, so let's say that you have, let's just keep it simple, let's say you have 4. All right. You might want a graph where, let's say, there's an edge here, and an edge here, and an edge here, but then there are 2 edges between these 2. And maybe this vertex connects to itself. A graph where that doesn't happen is called a simple graph. So you don't have any multiple edges like this, and you don't have any loops. In a simple graph, each edge is associated to an unordered pair of vertices. No other edge is associated to this same edge. So again, if you call these A, B, C, and D, this multigraph, this is not a simple graph, contains the edges AB and AB, so it contains AB twice. You know what? Don't have to do all that. As long as we all agree that order doesn't matter. Because that's another thing you can have. You can have directed graphs. All right. Maybe A can communicate with B, but B can't communicate with A. And in that case, you would want a directed graph. Let's see. It has BC, CD, and AD, and it also has CC. That's the loop. All right. When there is an edge of a simple graph associated to UV, we can also say without possible confusion that UV is an edge of the graph. Okay. A lot of vocabulary in this section. Here's the computer network. So a computer network can contain multiple links between data centers. So that's a situation where you might want to allow multiple edges. So you need graphs that have more than one edge connecting the same pair of vertices, and those are called multigraphs. When there are m different edges associated to the same unordered pair of vertices, we say that UV is an edge of multiplicity m. Oh, this is one of those moments where things that I'm talking about in different classes are all converging, because we're doing polynomials in my college algebra class, and so we're talking about multiplicity of zeros, right? Which means something different, but it's kind of related. All right. So that just means you have m different copies of a given edge. So like from Chicago to Denver, there are 3 edges, and so that edge has multiplicity 3. Sometimes a communication link connects a data center with itself, perhaps as a feedback loop for diagnostic purposes. So you send out like a test, to your own data center. And those are called loops. Graphs that that are allowed to include loops are called pseudographs. Pseudographs. They can also contain multiple edges, pseudographs. Okay, so all the graphs you've seen so far have been undirected. There's no reason to think about order. Okay, but like I said, sometimes you want your graphs to be directed. For example, in a computer network, some links may operate in only one direction, and those are apparently called single duplex lines. This may be the case if there's a large amount of traffic sent to some data centers with little or no traffic going in the opposite direction. So in this picture, let's see, San Francisco can talk to Los Angeles, but Los Angeles cannot talk to San Francisco. Okay. Chicago and Denver can talk to each other. All right. And by the way, I'm just looking over to make sure. All of the edges that you see in that directed graph are all different. In other words, you never have 2 lines going in the same direction between the same 2 cities. All right. So this would actually not be considered a multigraph because you don't have any repeated edges. These are two different edges. These are two different edges. These are different. These are different. That's going from Detroit to New York. That one's going from Chicago to New York. This one keeps tripping me up. But those are different. They're all different. All right. Okay, so a directed graph consists of a non-empty set of vertices and a set of directed edges, which are also called arcs. I'll usually just call them directed edges. In fact, I don't do a lot with directed graphs, period. All right. I don't think we covered directed graphs last year, at least not after this section. Everything, I just concentrated on undirected. Okay. Each directed edge is associated with an ordered pair of vertices, so u comma v and v comma u are two different things. Yeah?
Can you mix directed and then
Oh, yeah.
arc?
Mm-hmm. Yep. You can have a graph that has some directed edges and some undirected edges. Yep. Think about one-way and two-way streets.
Yeah.
It would make sense to have both.
What if we only have one?
One what?
Only one-way streets and two-way streets?
Oh.
Or you should just-
Only two-way streets would be okay, but yeah, only one-way streets, that would be kind of frustrating. Okay, when you depict a directed graph with a line drawing, you use an arrow pointing from U to V, so you've already seen that, to indicate the direction of an edge. Directed graph may contain loops, and it may contain multiple directed edges, but doesn't have to. So the example I showed you before didn't have either of those things. Directed graph may also contain directed edges that connect U and V in both directions. You did see that. All right. Okay. So here's an example where you have multiple directed edges, but no loops, right? I don't see any loops. No cities are connected to themselves. But you do have some multiple edges, like these two, those two. All right. Ah, there you go, mixed graph. Mixed graph contains both directed and undirected edges. Okay, this is probably the most important slide right here. It has the summary of all the vocabulary. So a simple graph has only undirected edges, no multiple edges, and no loops. And that's the kind that I'm going to concentrate on. Multigraph does allow multiple edges. A pseudograph also allows loops. Simple directed graphs have directed edges, but no multiple edges, no loops. And then you have directed multigraphs, and you have mixed graphs. All right. And now we just have some examples. Acquaintanceship and friendship graphs. You can use a simple graph to represent whether two people know each other. And there's this really cool example of a problem that I would love to show you, maybe later, involving friendship graphs. Okay, so you connect two people if they are acquainted, if they know each other, all right? Or whether they're friends. Each person in a particular group of people is represented by a vertex. Use an undirected edge to indicate that they know each other or if they're friends. And we're assuming that if, in order for it to be undirected, we're assuming that, you know, if I'm acquainted with you, then you're acquainted with me.
Yeah.
All right?
Say,
Yeah.
Facebook stalkers.
Right.
They're directed.
Right. The acquaintanceship graph of all people in the world has more than I think 7 billion vertices at this point, and probably more than 1 trillion edges. So they're estimating the number of acquaintanceships in the world at over 1 trillion. Collaboration graphs, that's where two people have worked together. All right, so for example, mathematicians, if they've written a paper together, would be connected with an edge. All right. Collaboration graphs are simple graphs. There's really no reason to make them directed. Either two people have written a paper together or not. Right? No multiple edges, no loops. So as soon as they've written one paper together, you just put an edge. You don't put another one if they write another paper. Vertices in these graphs represent people. Two people are connected when the people have collaborated. The Hollywood graph. So that represents whether two people have been in a movie together or a TV show. Hollywood graph has more than 1.5 million vertices. How many edges? Didn't say. Okay, and I was hoping it would say something here. Hold on. Huh, okay. Why didn't I mention Kevin Bacon in there? Yeah, so you know about 6 degrees of Kevin Bacon, right? So it's a game where, you know, I name an actor and then you try to find the shortest possible path from the actor that I named to Kevin Bacon, all right? So Kevin Bacon, you would just, if you wanted a cheat sheet for 6 degrees of Kevin Bacon, you could use the Hollywood graph. Just find Kevin Bacon in there and then try to find a, you know, path from whoever to Kevin Bacon. Okay, so what kind of graph from Table 1 can be used to model a highway system between major cities where there is an edge between the vertices representing cities if there is an interstate highway between them? All right, so the big questions are, should it be directed or undirected? What do you think? Does direction matter in that situation? I see one person shaking their head.
Well, you could condense a directed graph to an undirected one if you say there's flow back and forth.
Right, right. But if all we're trying to communicate is whether there is a highway that connects the two cities, that can be undirected, right? So, for example, the 5 connects, what, LA and San Francisco. So, nothing important with direction. You don't need multiple edges, right? We're just wondering, is there a highway or not? We're not going to count how many. And we're not going to pay any attention to loops. All right, because we're talking about 2 different cities. So that would be a simple graph. A would be simple because it's undirected, no multiple edges, no loops. There's an edge between the vertices representing cities for each interstate highway between them. So now what do we have to allow? What changes? Is it directed or undirected?
Undirected.
It's still undirected. Do you have multiple edges?
Yeah.
Of course you do. But you still don't have loops. No loops. So that's called a multigraph. There's an edge between the vertices representing cities for each interstate highway between them, and there is a loop at the vertex representing a city if there's an interstate highway that circles the city, like the 405 in LA. Kind of sort of like that. Okay, so if all we're doing now is allowing loops, that's called a pseudograph. So when you're doing these problems in the homework, which I will put up as soon as I can, just have to get it off last year's blackboard, you can, you know, look at this table. I'm not really big on how good are you at memorizing this vocabulary, all right? Especially since we're going to be mostly working with simple graphs. That was pseudograph. Pseudograph allows loops. All right. Okay. let's see, how close are we to the end here? Well, maybe we'll just do this one and then we'll quit. So 2 more examples for next time. Determine whether the graph shown, and I would have liked to have animated these separately, but this is all one image. I just screenshotted this out of the ebook. Has directed or undirected edges, whether it has multiple edges and whether it has loops, and then name the type of graph that is. All right. So everybody, is this directed or undirected? What is it? I said everybody. It's undirected. Does it have multiple edges?
Yes.
Yes. Does it have loops? No. And that's called a multigraph. Good. All right. Directed or undirected? Undirected. Multiple edges? Yes. Loops? No. So that's also a multigraph. Notice that there's also an isolated vertex over here. It didn't talk about that. All right, that can happen. All right, and this looks like something completely different. Directed or undirected?
Directed.
This is directed. Does it have multiple edges? Yes, I think it does. Remember, you have to look carefully at the directed ones. You have to see, are there arrows between the same vertices pointing in the same direction? And I think those 2 are. It's kind of blurry on here. Those ones definitely are. So yeah, this is directed. It has multiple edges, and does it have loops?
Yes.
It does. And so that's called a directed multigraph. A directed multigraph. All right. So I think I'm going to save the last 2 for next time, just so we, kind of have a. It's kind of nice when I find that if I save 1 or 2 things, kind of ties things together for next time, and then we'll get into 10.2, maybe 10.3. Yeah.
Was that last example, why would that not be a mixed graph? What am I,
Because it doesn't have any undirected edges. A mixed graph has both directed and undirected. Okay, we're done.